So come on, what are some ways in which they're similar? Okay, the model systems, okay, so they're characterized, they're sort of simplified representations of some system in a world, and they capture, in as much as they're dynamic modeling, they capture what? Change over time. Thank you. Okay, good. What's another way in which they are similar? How do they capture that change over time? Do they produce an equation that says, change in time varies as e to the minus alpha t? Is that always possible? No, they specify implicitly the behavior of a system over time. Implicit in the sense that they're describing how the change in the system occurs over time. And by simulating out the system over time, you see how those changes compound to yield system behavior. The system behavior is not described explicitly with a formula over time. It's not a function of time we can write down as a formula. Instead, it results as an emergent property of a series of relationships in the model, relationships that describe implicitly that behavior in terms of the changes that occur in a system over time. In a system dynamics model, we have changes specified in the form of what? Flows, derivatives, right? In an agent-based model, the types of change we describe will be more varied. We'll have events. We'll have state charts and transitions within them. And we'll have other mechanisms that we can hook into to describe change over time, to describe the rules by which the model changes over time. But the behavior of the model over time is the result of the interplay of those rules over time. Okay, we've stressed some ways in which they're similar. They have a certain state at any point in time, and that state evolves over time. You can characterize completely the state of the system at a certain point. How do we do that in a system dynamics model? What's the state of the system in a system dynamics model? The values of the stocks. We could freeze time, shut off our computers, come back, put in the values of the stocks, and as they were when we stopped it, and run forward, and it would be just as if we ran the model forward from the start. In an agent-based model, in principle, we could do something like that, but there's a lot more moving parts. There's a lot more elements of state. Riddle me this, where within an agent-based model is state stored? Where does the state lie? Yes, it lies within each individual. Each individual is responsible for their state. Remember, within a system dynamics model, the model is organized. People are subdivided up. We subdivide it according to characteristics, the state and their properties of a given person. So we'll have males and females, perhaps, within different sets of stocks. And then we'll divide the stocks further by whether people are susceptible, infected, or recovered, right? We divide up this information we store for each of those stocks a count. Do we not? We do. For an agent-based model, it's kind of like turning that on its head. We organize the model by individuals, and each individual maintains as its data not just a count of them, but a set of information about what state they're in, potentially with respect to one or more state charts. So that's the difference. In fact, we have many more moving parts. It's a much larger state space. Instead of having a state space composed of 3 dimensions, susceptible, infected, and recovered, remember this? susceptible, infected, and recovered, something like that, and the system at a given point in time is at a specific point in the space, and it may evolve over time. Remember that type of diagram? Now, instead of having 3 dimensions, one for each stock, we might have 3,000 dimensions with maybe 3 elements for each person, each of the 1,000 people in the population. That's a larger state space. And it turns out there's real advantages for using one modeling type or another for certain types of questions. Certain types of analysis, formal understanding, bringing certain types of control theory understanding to it, using Kalman filtering, you can only do with a model where you have explicit equations. But there's other sorts of investigation where you want to follow an individual over time. You want to have an intervention that depends on their history. You want to capture large parts of heterogeneity. You want to put them into networks. You want to place them in space and see them evolve. You want to model their decision-making based on their local perception of the situation. You want to model each car on a highway as it's going around the turns based on what that driver sees, applying the brakes and applying the gas pedal, because you want to capture where those traffic jams occur, as they do, at certain places where the visibility is impaired or what have you. If you want to capture that decision by each individual based on localized circumstance, the situated decision-making, an agent-based model or an individual level model in general can offer a much greater resolution, much greater ability to deal with such questions. But as we'll see later in the course, it's not a matter of choosing between them, it's increasingly a matter of weaving them together. Figure out which elements of your model are best fit to a particular model methodology. You don't have to decide up front which approach you want to use. You'll, over time, evolve that in a package like AnyLogic as you decide what's best for you next based on your hierarchy of priorities. Those, ladies and gentlemen, are some observations. But I speak in abstractions, and it's easy to fool oneself with abstractions. And it's easy for students' eyes to glaze over, and for it not to really sink in. So today, I would like to engage with you in a hands-on sort of way involving agent-based models. And I'd like to start with a model that's on our Moodle site, which those of you who are connected can go and retrieve. It's a model that's called Communicable Mobility, version 3 with networks. Okay? The machines stand on the table over there. They await your bidding. Those of you who are bereft of machines can get them or can pull up next to your neighbor and share their machine. But I'd like to make use of these machines. So if you could go to the Moodle site, you'll find a models area, and you should be able to download this. If any of you encounter problems there, please let me know. But it should be readily visible as one of the major sections here. So let's go to Moodle here, and I will see if I can follow along just to make sure it's all posted. Is anyone going to Moodle right now? Are you finding it? Yes. In the models area? Okay, good. I think the third model posted there. Okay. Now, okay. So if you download that and then you open it with AnyLogic, you should see something along these lines. And I'll move this screen around a little bit, but you should see a main class which consists of some population, and it has a graph up top, and there's some of these constructs, which we've seen before. What are these constructs here? Anyone recognize them? They're parameters. They specify assumptions about the model. And there's this thing here, which is shown as a lightning bolt, which is something we haven't seen before, which is called an event. This model is designed to systematically show you elements of the agent-based modeling vocabulary as it's represented in AnyLogic. There's a reason I'm doing this. The reason is that with stock and flow modeling in system dynamics, we had a very small but powerful modeling vocabulary. We had a small set of pieces that we could weave together in creative ways to model very interesting systems. You can combine in clever ways multiple elements into things like first-order delays, into things like aging chains, into things like coupled delay systems to get oscillations, etc. Combining them in creative ways yields some interesting high-level constructs. And you're typically conducting your analysis against those constructs. You're sort of looking at the value of stocks over time. You're looking at the values of flows over time. In agent-based modeling, we have a much larger modeling vocabulary. And we're going to be going through, in the next few lectures, systematically surveying that modeling vocabulary. What is the modeling vocabulary? With some of it, ladies and gentlemen, you are already familiar. Things like parameters, for example, you've seen before. But many of these things will be new to many of you. Events, state charts, representing populations, representing individual agents. Agents that communicate by sending messages to one another, receiving messages from another. Multiple types of transitions within state charts. Connections of people into networks. Embedding in space, having people move around, or these agents move around in space. Graphical user interfaces, data output mechanisms we've already seen in the form of charts, and we'll see more of them in the form of other types of things like histograms. And we'll be looking at some implications of the fact that these models are stochastic. We have, in short, a much larger vocabulary, and I would like to introduce you to that. In this model, which hopefully by now most of you have opened, many of you have opened, is designed to systematically showcase a couple elements of this vocabulary, many elements of the vocabulary. So we have before us parameters, we have before us populations, we have before us an event which fires off periodically. Let's go take a look at that. That event fires off periodically here. We're going to look at the properties window to see its characteristics. It fires off periodically to accomplish some task. In this case, it's a simple reporting task. A simple task of reporting at certain times, for example, how many people are infected. We have a population. This population is consisting, as I said, of agents. Let's go see what that looks like. You can see we have here a population of 100 agents. We associate the agents at certain locations, and we give them certain statistics that are defined over this population, where those statistics allow us to compute common quantities. Much appreciated there, closing that door. Maybe if you wouldn't mind getting that one too. We're vulnerable on both fronts. So we can define these statistics that operate over the population. They're cross-sectional. They depict the population, characteristics of the population at a certain point in time. Maximum or minimum of values. Think of maximum income, the minimum income, the average income, the sum up of wealth over the population, or what have you. The count of individuals who are infective. So we can define these statistics. But ladies and gentlemen, I've only shown you one piece of the model. What's the other piece I'm missing? The piece describing what? The individual, describing personhood, describing personness, as it is characterized by this particular model. And that's defined in this case in this person area. It doesn't have to be a person. It could be a car. It could be an animal. It could be a house. It could be a workplace. But in this case, we have it as person. So let's double click on that, call that up. And as I am wont, this being the Eclipse interface, I can double click and zoom in on this particular thing. We'll see within a person, we have these constructs that we know as state charts. Those of you here who have been here before will recognize these from UML, Unified Modeling Language. Those from computer science background, say who've taken 370. And here we describe a person's progression amongst the different states. They enter in this place where it's marked with the bar at the top there, with the bar and the circle abutting it. And you'll notice that there are these transitions within these state charts which are distinguished in terms of their properties. If we drew this out a little bit more, to be a little bit larger, we'd actually see more of their properties become visible. And you'll notice these little icons. They indicate different types of transitions that we'll be discussing. This is a message transition, a transition that whereby one agent can easily interact with another. This one shown with a little letter. This transition here from infectious to recovered, by contrast, is shown according to a rate transition, a transition that occurs at a certain rate, a chance per unit time, similar to a first-order delay conceptually. And here, I've been able to show these things by giving it a little bit more space. Otherwise, it doesn't show them. Over here on the right-hand side, we have two other types of transitions. What transitions lie before us there? One is a transition that's triggered upon arrival of an agent as it's moving when it gets to a destination, so it knows when it's arrived. And it will undertake some action then. And then finally, a transition with this little clock, which is depicting a timeout, a transition will fire after a certain precisely specified amount of time. These transitions will each have code associated with them. And by the way, I'm trying to give some of you folks who are going to be engaging with these types of models immediately for your projects a little bit of a leg up on these things by kind of doing a grand tour before we discuss particular subtopics in detail. Because some of you might want to use mobility immediately. Some of you might want to use elements of spatial embedding. Some might want to use elements of networks. And I want to give you an indication of how these things fit together to combine these elements of vocabulary combined to form mellifluous sentences. So if we look at one of these transitions, we'll notice that we can associate it with some semantics for the transition. In this case, it's a timeout transition occurring after exactly time 1. And at that time, it will call off and apply a network. It tells main, hey, go apply a network here. And here we have, with this transition, when the agent arrives, it will simply come out and it will re-enter this state. And when we re-enter this state, we'll move ourselves to a different location. We'll set our rotation so we're not moving around it in a really obvious way, rotationally. In any case, we're moving to a new location. So this is an element of spatial movement. So let's see how this all fits together. We have infection here. People start susceptible for the most part. They go through an infection phase, they recover, and there's this movement. So when they come into the state, they start moving. When they arrive at their destination, they come back into the state and start moving in a different direction. And are normally perturbed according to a Gaussian perturbation, according to a perturbation that sort of knocks them off a little bit, tells them go over there. So let's go see what's happening here. We see sort of a set of little balls bouncing around in sort of a chaotic motion. It's sort of a Brownian motion. And these balls are interacting. In this case, we see most of them are green. When they come close to each other, they form network connections. Can you see that? As they're coming close to each other, we can slow this down, of course, by adjusting this thing here. And as we'll see, when things have close passes, they're connected briefly. And those brief connections, ladies and gentlemen, will provide the basis for infection transmission. So here we're starting with certain people infected, and they're going to be moving, and over time they're going to encounter others, and that infection will be passed. And it's disseminating here, not in some purely type of random mixing, but according to mobility. It's disseminating through this population, and over time some number of individuals will become infected and then ultimately recovered. So here we have a model, ladies and gentlemen, that illustrates elements of state chart transitions, elements of movement in space, people having locations, elements of a population which can compute statistics over it that describe its current state, such as the number of people currently infected, and then constructs which will display that information, not in a way that modifies the model, but which will help us understand what is going on. So, for example, this guy here can call this statistic count infective in the population to compute the number of infective people. So here we have a plot up here on the diagram that depicts the number of infected people over time. That plot should remind you of something, should it not, within a system dynamics model? Many a time have we constructed together those sorts of plots. And even additionally, have you done so within your problem sets? We can aggregate when we have a lower level model like this, when we have a model that's articulated at the level of individuals, we can always sum up to get aggregate quantities. But we can do so in a way that's peculiarly flexible, that allows us to subdivide those totals by arbitrary measures. We can count up the number of people with this distinction, that distinction. We don't have to pre-bake those distinctions into the model, but we can total up at our leisure individuals who match this characteristic or that one. We could have individuals even distinguished by age at a continuous level, not just age categories, 0 to 4 years old, 5 to 9, 10 to 14, but instead we could characterize their age on a continuous basis and total up the number of people in any number of different age categories. We don't have to bake those age categories into the model as we would with an aggregate system dynamics model. We can total up the number over time that match certain characteristics and see how that plays out, while also being able to capture the spatial factors that govern infection, that govern that behavior. So you could take this model and elaborate it in any number of different directions. But my goal in showing this to you is to illustrate a model that captures many, not all, but many of the elements of the agent-based vocabulary. Those of you who are embarking now on projects that involve agents, for example, will want to consider making use of this basic type of model in stimulating your thinking about how you might capture things like mobility, or how you might capture things like spatial embedding, or populations, or state charts, or events within your model. Okay? So what I just showed you was kind of a model that wove together a bunch of these to accomplish some overall tasks. Any questions about this model before we go in to examine how we build up a model like this with a particular emphasis on certain critical features of this model, before we dive down into elements of this vocabulary? Are there any questions at a high level about this model or about this sort of modeling? The sound of silence. I'll take it as a no. So, ladies and gentlemen, some of you may wish to elaborate that model on your own. I am going to close it, and we're going to begin building up a model, our very first model built from the ground up. No one wants to ask a question first? Okay. So let's go build a model. Okay, ladies and gentlemen. We're going to build up a model which exhibits one of the defining strengths of agent-based modeling. The fact that it's able to capture heterogeneity, capture ways in which agents in a population differ considerably. How do we capture, ladies and gentlemen, heterogeneity within an aggregate model, such as a stock and flow model? How do we capture the feature that people are different within the model? There are different types of people circulating. How do we do that? Add more stocks. Yes, that is the key thing at a certain level. To adding more stocks. Now we can fancy it up in different ways. Some packages, which some of you, as some of you may know, allow you to subscript a stock, but fundamentally we're dividing up stocks. So if we want, for example, males and females kept track of separately, so we want to know how many there are of each, we generally give them a separate stock. Maybe we want to capture the spread, the impact of a spread of infection in males and females. And if we wanted to do that, we could have groups of males, groups of females. This would be sort of male SINR, female SINR. And there would, of course, be some interaction between them. A female might develop the infection from a male and vice versa. But we divide them into stocks. If we want to capture people of different ages, we divide up the population into different age categories, for example. So this might be the 0 to 4 years of age at top, and then 5 through 9, and then 10 to 14. And there'd be some mixing between them. 0 to 4-year-olds would spend a lot of time together, but they'd have some mixing with their older siblings. They'd have some mixing with their parents, a lot of mixing with their parents. And so we describe our so-called mixing matrix that would say what fraction of the contacts of 0 to 4-year-olds take place with those who are 5 to 9, 10 to 14, 15 to 20, to 19, etc. Right? And we can do that. But the overall point, which was articulated earlier, is that to capture heterogeneity, be it static heterogeneity, like sex, male, female, or dynamic heterogeneity, age, where you actually would be aging here from one age category to another over time, to capture that, we divide people up in different stocks. Why is that? Why is that? Why can't we just do it all in one stock? Because stocks are what? An individual stock, the flow out of the stocks have a certain property associated with them. Stocks, everything in a stock is considered to be, sorry? Yeah, it's well mixed. I think you got it. I mean, it's well mixed. In other words, it's a memoryless thing. It has no memory of when people entered it. Once you come into the stock, it doesn't matter whether you've been there 1 day, 1 year, in terms of your chance of leaving. The same chance of leaving per unit time, call it alpha. The same mean time in that stock, call it tau. You could phrase it as either of these, where tau is 1 over alpha, right? That's regardless of when you came in. It's memoryless. It doesn't care when you came in. There's no memory of that. Once you're in there, you're all in the same boat together. So stocks are used to capture sort of groups that are pretty darn similar to each other, sort of interchangeable. And it doesn't matter how long you've been in there in terms of your chance of leaving. Let's suppose, so let me ask this, ladies and gentlemen. I like to use these lectures to talk about the things which fall through the cracks in videos and things which are better captured together. So let me ask this, my silent companions. If we want, is it true that a system dynamics model as a whole is memoryless? That as a whole, that all constructs in system dynamics are memoryless. Is that true? I said a stock is. Stock doesn't differentiate for the people in it when they came in. How about a collection of stocks? Is that memoryless? Suppose I put a set of stocks like this with flows between them, a so-called aging chain. And now I consider that as a block. I consider it as a unit. The entire thing, right? When you go out of this, so suppose we have some input into here, people flowing in at different times. Does their chance of flowing out in a given year depend on how recently they flowed in? Yes, it actually does. If they flowed in very recently, where are they more likely to be? They're more likely to be in this one, right? This first stock in the chain. If they flowed in a long time ago and haven't yet left, they're more likely to be in this one. So here, it is true that a single stock in system dynamics is memoryless. It's not true that whole collections within a system dynamics model of stocks are memoryless. By no means. We can capture in memory full characteristics. We just have to do so by breaking people up into different stocks. We can capture people with any or shorter amount of time, medium amount of time, longer amount of time. If you want to capture the fact that people who have had diabetes for a long period of time are more likely to develop heart disease, or someone who has had HIV infection is more likely to develop AIDS after a long period of time, how would you do that? You'd do what? Yeah, you'd have different time range slots. You could have 0 to 1 year, 1 to 2 years. Would they all have to be divided by the same length of time? No. You could have 0 to 0.5 years, 0.5 to 1, 1 to 2, 2 to 4, 4 to 10. There's no problem with that. Each could be a first order delay leaving it, right? So if you had a stock that was 5 to 10, people who have been there 5 to 10 years and your time unit was years, what might be the tau associated with that stock? The mean amount of time you spend in there. If that stock represents people who have had diabetes for 5 to 10 years, what fraction of that population would leave every year? About 1/5, right? It's kind of for 5 years worth of people. About 1/5 leave every year. The assumption is they're kind of well mixed. Once they come in there, we're not really particular about whether they came in a year ago or 5 years ago, but about 1/5 of them leave each year. If it's a stock representing 10 years worth of people, about 1/10 of them leave each year. Does that make sense? Okay, that's in system dynamics. So, ladies and gentlemen, heterogeneity, however, is limited here to disaggregation. Because we're dividing people up into different stocks, we have to divide them, if we have a construct like age, or income, or education level, these things being more continuous in nature. You can have, quite a detailed income, or quite a your age can be specified very, very precisely. But we have to divide up into categories. Birth weight, we have to divide them up into broad birth weight categories. We can't sort of keep their precise birth weight in order to divide them up into these different stocks. I'm glossing over some things. There's some things called coflows that allow you to do some interesting tricks with the average birth weight or what have you. But by and large, you're limited to categories, dividing people up into categories. And ladies and gentlemen, this goes on for a certain amount of time. You can divide people up to age and sex pretty comfortably, maybe even throw in ethnicity or something. But once you start keeping track of many types of things, it starts to blow up. I mean, already larger and larger. You can imagine here we have, infection status and age. Now, if we wanted to do sex, now we would have a whole other dimension coming out of the board, right? Almost like we have another layer here. And then if we wanted to do ethnicity, wow, now we have now suppose we wanted 5 ethnicities, it would multiply the model by 5, right? Adding sex would multiply it by 2. So you get this kind of combinatorial blow up as you try to record more and more distinctions because you have to divide them into categories. And system dynamics modeling has many strengths, some unique ones that really recommend it for certain things. But capturing heterogeneity, capturing these distinctions is not one of its strong suits. It's not one of its areas where it's most flexible. Agent-based modeling, it's very flexible. Very flexible. So ladies and gentlemen, let us consider this. So let's go create our first model. File, new model. Here we go. And we're going to create a heterogeneity model, 394, 858. You don't have to call it that. T1, 204. Okay, there we go. Boom. Okay, so I just created it. How did I do that? File, new model. Okay, I think we've done it many times before, so I didn't emphasize it. I'll try to go slower in subsequent steps. File, new model. Okay? People comfortable with that? Okay. So I just created a new model. So ladies and gentlemen, we want to create a model. We've created a model many times before for system dynamics models. How are we going to create a model that's an age-based model? What's the key feature we're going to be adding that distinguishes this? The presence of a what? If we look at even just this hierarchy over here on the left, the project hierarchy, there's something that distinguishes quite strongly a system dynamics model, one that's purely system dynamics, say the second one here, from one that's an agent-based model, like this fourth one down. What's that key thing? The presence of an agent class, this thing that describes agenthood, agentness. Okay? So, ladies and gentlemen, let's go add an agent class and let us travel where we have never traveled before. Okay? Okay, so, new agent type, and we will say person. Okay? Well, I will say person. The things we're saying are most best suited for people. Okay, so now we have a person. We have an agent class. And this class is going to describe agenthood. It's going to describe sort of the theory of what it means to be a person with respect to this model. Remember, all models are simplifications. Models are thinking tools. They're useful because they simplify and let us think through, in precise terms, the implications of our assumptions. A small number of assumptions often can yield very interesting consequences. But, and because of that, we're not going to put all features in a person, but we're going to put some features. So, ladies and gentlemen, I would like to take this person, I would like to give them an appearance. Just so this is going to be convenient so we can see them. I would like to go down, see here in the palette, there's a thing called presentation, and I would like to lend them an appearance. Maybe we want to give them an appearance that's based on a simple circle. So I just dragged in a circle and I placed it at this origin, okay? So I just went down to this and I went to circle, to oval, and I dragged it up there and I resized it and put it here. Why there? Because this is the point, by putting it there, this is kind of the frame of reference for the agent. if we put it at the crosshairs, what that means is visually they'll be located at their logical position. If we put it offset from this, say just to the right, but along that line on the top, then they'd be appearing systematically to the right of their logical position, which can be sometimes confusing. And like if you're trying to debug a model, it's confusing. Okay, so we just drag them there. Are people okay with that? Okay, ladies and gentlemen, so we just drag them there. Now I'd like to do something further. And by the way, you notice they added that before doing this next step. It's potentially important in this version of AnyLogic. I'd like to go back to main. Main is going to be the stage on which these agents strut. It's going to be the location where the population of these agents will live. And to add a population, ladies and gentlemen, watch my mouse. To add a population here, can anyone tell me how to do it? Those of you who have seen this before? What do you do? The silence continues. Okay, so I'm going to drag it. So I just dragged it over, click, drag, drop, and I'm going to say population. This is going to be, at some point, this is going to be second nature. It should be. It should be second nature to you. Drag, and then I have to say it's a population of agents. It's not just a single agent, it's a population. And we're going to make this, ladies and gentlemen, for right now, a population of size 100. For the moment. The software engineering me protests. I'm having an internal struggle. But for now, we will, my pedagogy is winning out over my software engineering aesthetics. Okay. Here's a population of agents. Okay. Ladies and gentlemen, I am going to now suggest that we go and we're going to run this model, and we'll see something that's not terribly exciting, but it's something. So we're going to run it here. How did I do that? Well, it's the same way we've been running the system dynamics model. So I right-click on it and say run, for example. And we'll see something. We'll see, okay, there's a population of 100. We'll see that there's these circles here. More interestingly, in this navigation menu, I could see here's a population, different population, and I can scroll through them. But they're all the same right now. They're not different in any way. They all are illustrated by the same little circle here. So ladies and gentlemen, we're going to do something which will make it obvious that there's a population. And this, too, is a point that you're going to want to pay attention to. It's going to presage later work. Let's go to main. And we're going to actually lay these people out in space. How will I do that? Go to main here, and we will go down here, and we will say that we're going to have a layout type that's random. Okay? We're going to lay them out randomly on the screen. How did I do that? I clicked on main. I dragged in properties down to do layout type random. Okay? I'm trying to go a bit slower, because I got some feedback from some people in the class that it's hard to follow my hands. So I'm trying to go slow. So what did I do? I clicked on main. I dragged down to this area that's called environment for other agents, and I said layout random. And now you folks should see how to lay it out, right? Do you see this? Could you run it? Okay, run it. For the most part, I'm not going to do quite this level of tutorial-y stuff, but I want to talk about some of these implications. So you see it laid out? Do you see it laid out before you? It stands before you in uniform glory? Okay? Okay. Silence returns. Okay. So, ladies and gentlemen, we've just seen that there's a population. There's a population of people laid out on the screen. We've laid them out randomly. Another way we could have done that, incidentally, that actually is more general, would have been if we had gone up here and associated with the population, we could have said lay them out at a specified X, Y, Z point and had values for that, okay? Okay, so ladies and gentlemen, I would now like to give these people characteristics. I want to give them an age. An age. Okay? So, how are we going to give people an age? Can anyone think about a construct we've already used in other models? Yeah, okay, great. I like hearing that. It's a type of variable called a parameter. So we're going to go to person, and we're going to add that in. It's a parameter called age, okay? And what type will it be? It'll be a double. It'll be a double precision value, 3.2. It'll be, 42.537, okay? So it's a double precision value, okay? Ladies and gentlemen, I would now like to go and associate them with an age distribution. The age is a characteristic of personness, the fact that they have an age. By contrast, the particular distribution of values for that age is not a characteristic of the person per se, but it's a characteristic of the population in which they're embedded. Certain populations tend to be older, certain tend to be younger. Population distribution, age distribution in Saskatoon is quite different from the age distribution in New York City. So we're going to take a population here, and in age here, you'll notice that we can specify things. And it will give us some hints with this little, if you go here, I'm clicking on this population here, and it says, we could use index to refer to what's the number of this person in the population. But I'm going to simply put in an expression here. I'm going to put in a little formula that says it's going to be uniformly distributed between 0 and 85. Okay? Now, I think I've told you before, you can do control space here, and it will actually fill out possible values, which it's doing quite slowly here. It'll fill out possible values that I could use here, and it will describe the meaning of each of these using Java docs here. And each of them, has certain meanings. This is going to be between a minimum value and a maximum value, okay? So I'm doing uniform between 0 and 85. Okay? People comfortable with that? Okay, so ladies and gentlemen, let's do that. So now each person's age is taken from this distribution. So let's run this. Okay? And here we have the same population laid out, but if we go down to the level of a person, we'll find, for example, this person is 44.55, 24.923. Different people in the population have different ages. Does that make sense? We specified age. The fact that people have an age is a characteristic of their being a person. What their age distribution is, that is the type of English up with which I will not put. The age distribution with which they're associated is specified by the population. Okay? Okay. Ladies and gentlemen, I want to show you... Yes? Question? Sorry? What's that circle for? The circle here? You mean around this? You mean like why is there... Oh, you mean this circle? Okay, that's a great question. So why is there a circle here? After all, okay, so Anahita has put her finger on a very perceptive question. Perceptive at two different levels. Perceptive because there's a circle in a place that it doesn't seem to belong. After all, where did we add the circle, ladies and gentlemen? To whither did we add the circle when we added it? We added it to person. And this is the deeper thing to which Anahita's point, to which Anahita's question points. you have to be very careful when you're doing things, these models, about where you're changing it. Where did you add that? Where am I going to, whither will I add this? To whether it's to person or to main. You want to be very clear in your mind. Am I adding this to person or main? And make sure you're adding it to the right class. We actually added that circle to person, but then Anahita picked up, quite rightly, that, no, wait a minute, there's this circle up here. Where's that circle coming from? After all, person has a circle associated with them. We could have made them all sorts of shape. We chose a circle for this introductory lecture. But now suddenly we have a circle here. What does this circle represent? Ladies and gentlemen, I'll tell you what it represents. It represents the frame of reference for where that population of agents will be displayed. So if we move this over here, what it will mean is the agents will be displayed, so X will be relative to this point. So positive X's will be here, negative X's will be over here. The people's location is used to display them on the screen at a point relative to the location of this origin. Okay? So a negative here will be over to the left of that point. Now positive will be here. By moving this around, we can choose where we display them. Is that helpful? Okay. So ladies and gentlemen. Okay, so let's go one more. Now, this is key. This is a key conceptual point, too, that I want to drive home. We want to now, so we've already added a continuous construct, age, given people continuous age. That would not be something done readily in a system dynamics model. We'd have to divide up to age categories in an aggregate model. Now we want to add sex as a characteristic. We want to give people a sex, okay? Want to give them a gender, so we're going to drag in, it will say sex. Ladies and gentlemen, if we wanted to add sex into an aggregate model, suppose we had 3 stocks in the original model, susceptible and factor recovered. Suppose we want to keep track of sex. How many stocks would we have now? 6. Doubles the size of the model. In general, will dragging in a new parameter double the size of a model, for example, a new binary parameter? No. Will dragging in a new parameter could take on 100 values, multiply it by 100? No, it's just one more data item to be kept track of, right? It might increase it by 10% or something like that. The point is you're not disaggregating the model to capture heterogeneity. You're capturing heterogeneity within each agent, just by storing a bit more data, a bit more information associated with that agent. We could add a parameter that's continuous, the income, and we wouldn't need to multiply the model size hugely at all. Just be a bit more data kept track of. Do you appreciate that fact? Do you understand that fact? Okay. Okay, we want to add sex, but how might we encode someone's gender? Riddle me several ways. A string. An enumeration. I like that aesthetic. Who said that? My glasses are off to you. Had I a hat, I would doff it. Enumeration. Why would enumeration be more favorable than a string?
Because there's only a certain set of possible.
Yeah. Yes, that's the most critical reason. I mean, you could argue also that it takes less space. It doesn't require, allocating space in the heap for some number of characters. But the most critical advantage, as far as I'm concerned, from a software engineering perspective, is if you're less likely to make a mistake. If you kept it in a string, you might say capital M male, lowercase m male, all capitals, M-A-L-E, all capitals. All those would be perfectly reasonable way to encode it. The point is you need to be consistent, and there's nothing that enforces that consistency. With an enumeration, it's enforced. It's required. And that's really important. Enumeration is really valuable. But there are other ways, too. How often in biostatistics, those from you outside computer science, speak with me as in one voice. If you're in biostatistics, how do you often encode sex? Okay, yeah, 1 and 2. 0 or 0 and 1. Dangerous again, because it's not clear what 0 means. If Yuli looks at 0, he won't immediately know what it means. I would have to ask, what does 0 mean? If you encoded provinces as, 0, 1, 2, 3, 4, now you could assign a sex to a province, and it would say, perfectly fine, 0? It could be Newfoundland, or it could be male. You don't really, there's nothing to keep track of that. Whereas in enum, it keeps track of it. It keeps track of it in a firm way. So, let's add an enum. My hat remains off to you. Okay, so let's add an enum. How do we do that? Right-click on this, new option list, and let's call it sex with a capital S. You notice this one I called sex with a lower s. It's a particular sex. Names matter. Names matter. Those of you who take 371 will hear that again. Names matter. Names are very important ways of communicating information. And generally, when we name things, we use lowercase to mean a particular one and a capital to indicate sort of a whole class of possible things, like a class or enum. So we're going to say males and female. Male and female is going to be the sex. Okay? Okay. Male and female. How did I do that? I right-clicked here and I added a new option list. Okay? And now we could simply say the sex of this person is not a double, it's a sex. It's an instance of sex. It's either male or female. Does that make sense? Yes. Okay. So, it's a reflection. We didn't have to double the size of the model. Adding a bit more heterogeneity here is a lightweight exercise in terms of model size. But it's lightweight, ladies and gentlemen, in one other respect too. If we wanted to add in sex, if we had distinguished people in this diagram up front on the blackboard, on the whiteboard, and by age category, and by infection status, we want to add sex. We would double the model. Why double it? Because we need to do what to every stock? And flow, in fact. We need to do what? Yeah, we need to create a new version of it for, say, for males and then for females. We need to have two of them where there once was one. And in short, it's not only doubles the model size, it's a global operation, meaning you have to go and change all these different things in the model. For each and every little piece of the model gets touched by it. Every piece of the model gets touched by it. Now, if this is the set for males and the set for females will be separate, it requires going and changing every piece of the model. Here, it's a very local operation. You add it in. It doesn't really require to change many things in the model. It's very localized in its impact. It's very surgical, precise. Another reason adding heterogeneity or removing heterogeneity is much more flexible in agent-based models. Do you understand that point? Subtle point. Okay. Okay, so ladies and gentlemen, we added in sex. Now, what do we need to do, just like we did for age, what do we need to do for sex? We need to specify a distribution over it, some distribution here. Okay, so there's many ways we could do this, ladies and gentlemen. One way would be to say sex.values.random. Actually, you say random from this. I think that's right. Yep, random from sex.values. This would be one way. There would also be another way where you could simply flip a coin, and if it's one, it's males. Otherwise, if it's heads, it's males. Otherwise, it's females. I'll leave it with this for now, and let's run the model. Okay. Okay. Hey. Oh man, it's. Okay. Sorry. I did a boo-boo. I should have said sex.values, and this is actually, sorry, it's a method call. It's It's not a property. Sex.values begin paren, end paren. See up here, this is going to be increasingly important for the agent-based component. See this build model thing? Please press it early, press it often. It will tell you if there's a problem. Okay? Okay. So this is random from sex. Can you see, folks see that in the back? Okay. Okay. Here we go. So run. And now when we go, we should be able to look down. This here's a female is 3.346, male 16 point, and so on. Okay, ladies and gentlemen, we've seen aspects of heterogeneity. Ladies and gentlemen, now I want to show you something further about AnyLogic that you'll want to take advantage of in your projects for those who are pursuing them, and that you will take advantage of also in your assignments. Go to person, those of you pursuing assignments rather than projects. So go in person, and we're going to make it so someone's appearance depends on their properties. Mm-hmm. Where would their appearance be given within this model? Where's their appearance shown right now? It's in the oval. So you go to the oval, and if you scroll down, you'll notice that there's this thing that says advanced, and you can open it, and actually, we don't even need that right now. We will be interacting with it later through onClick. But for right now, we're going to use these properties in position and size. So click on the oval, go down to position and size, and in this property that says radius, see where it says equals here? Do you see that? People comfortable with that? Instead of making it equals, click on it and making it this thing which indicates a dynamic value. And we're going to set the radius equal to their age. Okay? And we are now going to set their color, which is given up here by fill color, in a similar way. So what do you think I have to do here? Okay, yes. And for fill color, what do I have to do to be able to do that? I need to click again here to turn it to this dynamic property, okay? I'm not going to be babysitting you on all the lectures like this, but I want you to get familiar so you can start to do this yourself pretty quick. So I'm trying to teach you some basic skills in this, okay? You have plenty of videos where I walk through this in great detail, and we're going to try to use the lectures for more conceptual material and material that's tougher. But you should be aware that for basics, just to kind of get going on your projects or problem sets, you want to know about these things. So fill color, let's make it so if they're male, they'll be gray, otherwise females will be yellow. So if their sex equals sex.male, male as dictated by the sex option list. If so, how do I say that in Java? Yes, question mark operator. If so, we'll make them gray, otherwise we'll make them yellow. Okay? And you can use this to compile it. Okay? So what this is saying is, it's kind of like a if-then-else statement, but it's not a statement. A statement tells you to do something. It's a command. Do these things. If this is true, do these things. Otherwise, do those things. This is not a command. This is saying, if this is true, use this value. Otherwise, use that value. This is an expression. This is a formula that gives a value. So it's not an if statement you use. It's a sort of if expression. We call this a ternary expression because there's three pieces. This, and this. So if this thing is true, if their sex equals male, then we're going to use gray, otherwise yellow, colon, there to separate those two. Does that make sense? You folks have seen that before from computer science? Only in this class? Yeah. My software engineering would tell me create a function. and have the function return a value, and then just use, my color or something, call that function. But this is reasonably clean way of doing it if you just have two possibilities. Okay, so ladies and gentlemen, let's run this thing. What should we see now? Okay, yeah. Okay, and if we go and we look at a particular person, for example, here's a male who's older, here's a male who's younger, here's a female. Their colors are varying according to their characteristics, right? Okay, ladies and gentlemen, I want to draw attention to this. This is a very important principle and one I expect you to understand. What we just saw was an example of declarative programming. And much of AnyLogic is like this. Much of many packages coming out today, even if you folks never go on to use simulation packages in your professional careers, even if you're left in that sad fate, you will encounter, if you're going to computer science, a growing number of packages where you specify at a declarative level what you want to occur, and it takes care of the how. It takes care of making sure that that will happen. It's associated with trends in software engineering, like inversion of control, dependency injection. You see it cropping up in area after area that they use what's called the Hollywood principle. Don't call us, we'll call you, okay? We will arrange the framework that will guarantee the properties you want. You fill in the missing pieces, and we'll make it hang together. This is increasing the model of computing. You're not building things from the ground up. Rather, you're fitting into systems, whether they be sophisticated web application servers like WebSphere, whether they be into transaction management systems, whether they be into GUI programming systems, simulation packages, area after area. You're filling in the details, and it's taking care of wiring the things up and making the things you want to be observed actually happen. Here we're specifying the fill color. It's making sure that happens, that this turns into something on the screen. We're specifying the radius in terms of age, and it's specifying that make sure that obtains, that happens over time. And let me assure you folks that if these things were evolving, if we had people's age changing, that would be kept up and it would change over time. It would actually show it over time as their age evolved, okay? So here we're going to see that we can specify these pieces, and AnyLogic will sort of make them happen. We specify the properties we want to hold, and AnyLogic takes care of sort of maintaining the underlying mechanisms, the plumbing to make sure that happens. Okay, so we could go into some more details there, but suffice it to say that here we have a declarative programming environment. We have these individuals distinguished according to their characteristics, and we can have these characteristics depend on one another. We could have an income, for example, whose value depends on the person's age and sex. And we would use a formula for income which then depended on self.age, self.sex when you wrote out that formula. I'm not going to be showing that. You can find videos where I talk about it online. The important point is we can capture elements of heterogeneity, and we can do so and display them in a graphical sort of way. Okay, so we're at an important pass here, and I'm going to cover one of three things in the closing couple minutes that we have. And I'm going to pick my path here. So what I'd like to introduce to you now, the next very important point would be I'm going to introduce a state chart. And I'm going to actually ask you to watch a video on state charts. But I'm going to introduce a state chart associated with, so this will be state chart, and it will be state chart for their health, okay? And I'm going to have them go into a state. So I just went down to the state chart area here, and I dragged in an entry point, and I'm going to have them go into initially a healthy state, and then I'm going to drag in here an ill state, okay? And connecting these two states are going to be transitions. So I'm going to drag in a transition here, and this transition will be becoming ill. And I'm going to click this so that it shows that name. And this will occur at a certain rate of 0.05, okay? So every 20 years, they'll become ill, and they'll have a certain chance, every 20 years on average, they'll become ill, and then they'll have a chance to transition back, okay? Here, and this will be with a rate of 0.01. So I'm trying to illustrate an additional mechanism by which people can change state here, okay? And now, instead of having people's, the overall color, the fill color of the entire circle be dictated by their sex, I'll just have that dictate the boundary around the circle, and we're going to have the color be dictated by the state that they are in, okay? So I'm going to show you some mechanisms. I'm trying to get you going so you can start to work on problem set 2, which will be introduced in just a few days, or you can be working on your projects. So ladies and gentlemen, with an eye towards introducing an element to the AnyLogic vocabulary, what sort of mechanism would we use to communicate what states that they're in? Suppose we had many states that they could be in. What might be a way that we could communicate what color to make this based on what state they're in? Can anyone give me a way? So if we wanted to set their color according to the state they're in, one way would be to use something very similar to what we have here, a sort of expression that would dictate this. It would get pretty unwieldy after a while. It would grow large and unwieldy with many conditions. It would be better to have a function, a method. But this would be just one way. What's another way we could do it? If we wanted to keep track what state that they're in, and, keep track of a certain color according to state, what could we do? When they enter the state, we could do what? Well, we could change their color. So what we're going to do, with an eye towards introducing a mechanism here, we're going to go to this general mechanism. We're going to put in a variable called current color, okay? When they enter a healthy state, we're going to set, in current color, to be a color, it should be of type what? Anyone? Type, well, type other, and it would be color with a capital C. Its value could be one of possible colors. It's a reference to a particular color. Capital C color is color hood. It's colorness. It describes all set possible colors. And this will be a particular one of these colors, a reference to a particular color. Okay? And when they come into the healthy state, so I just added this. How did I add it? I added it from this general property. I dragged a variable over and called it current color. Okay? And now when they enter the healthy state, we're going to set current color to be green. So current color equals green, and then semicolon. Semicolon is used in Java when it's a state. It's finishing a statement. It's a command. Do this. It's not just a value, 30. It's a command, okay? Those not from computer science background will want to appreciate that. And what do I do so this is when they enter that state, this will occur. When they enter the ill state, suppose we want them to become red. How would we do that, ladies and gentlemen? Okay, current color, and where does it go? Entry action, right? Current color equals red. Okay, good. Okay. Good. Ladies and gentlemen, we're now going to, what's the final thing we have to do in order to make it actually be actionable as color? So I said it's their current color. What do I mean to enforce that that's actually their color? Where do I go? Whither do I look? Sorry? Where do I go? To the oval. Good. And now, where it says fill color, I want to make that actually their line color, the next one down. So I'm going to take this and then click here just to make it dynamic and paste that there. And I'm going to make the line width be 5 points, so it's a nice thick line. Okay, 5.0 points. Looks like it's happier with that. Well, it doesn't fill it. Okay, and then the fill color. What will I put in for fill color now? Riddle me this. What do I put in for fill color? Current color. Okay. Okay, ladies and gentlemen. So we now have an oval whose size is dictated by their what? Age. Whose boundary color is dictated by their sex, and whose color, the fill color, is dictated by their state. Okay, so ladies and gentlemen, shall we compute? Thank you. Okay. Okay. It's Christmas time in the city. Okay. So what's happening? Can anyone describe for me? They're oscillating between healthy and ill. The rings around them, of course, are stable because that indicates male or female. The actual circle's color is dictated by their current state. Very good. Okay. I am going to further modify it and ask you to puzzle over this until you watch the next video for Thursday. So, ladies and gentlemen, I want to take this state transition here, and we're going to change this to be a timeout transition. So a rate of 0.05, what is that correspondent to in terms of mean time healthy? 20? Yes. Because this is exactly, who said that? My second hat will be doffed to our guests from the School of Public Health, one of our several guests in the School of Public Health. So that's exactly right. So there's a chance per unit time of 0.05. Where have we seen that before? We've seen that whole computation of a chance per unit time and having a corresponding average time in the stock. Yeah, we saw it for first order delay. Same reasoning here. You have a chance per unit time of 0.05. It's continuous time. So your average time there is 20. So let's turn it now to a timeout of length 20. And similarly, the reverse one here, reverse transition, a rate of 0.01 is now a timeout, should be a timeout of what? Let's make it a timeout of 100. Oops, sorry. Oh man, I screwed it all up. It should still say a rate of that, but I'm gonna change this to be timeout of 100. Okay? Okay. Now never mind the limited plausibility of the physiology depicted. And we also should really go and change the time units, not from minutes, which would be a very grim health situation indeed, to be years. Okay, so ladies and gentlemen, we changed these to be timeouts. In this case, it would be a timeout of 20 years. In this case, of 100 years. What should we now see as we run this? Can anyone predict? Can anyone prognosticate?
They changed together.
Okay, they changed together. Why do they change together? I'm speeding it up a bit. Why do they change together?
Because it's a timeout and everyone starts.
It's a timeout. They start at the same state, and after exactly 20 years, they're going to become ill, and exactly 100 years later, they're going to recover, and then the cycle repeats, right? Okay, so you're going to learn in a video a little bit more about the different types of transitions in AnyLogic, which we're going to be using systematically in the course of this semester. I think I will leave it at that for today. I would just note that we barely scratched the surface of these basic mechanisms. Those of you who are interested may be interested, for example, in having the circle size grow as this person's age is increasing. Instead of keeping track of age as a fixed thing, we could keep track of when they were first created, and then the difference in the current time and that time will be their current age, and we can make that circle grow. But for next time, we'll be hitting on several additional mechanisms and using them to give a new lens to some of the same phenomena we depicted at an aggregate level in a system dynamics model we'll depict at a more fine-grained level in an agent-based model. Okay? So that's all for today. I appreciate, and I received various hand-ins physically on problem set 1. I'm going to be releasing problem set 2 within the next day or so for those who are pursuing them. And this lecture in particular should help you get started on some elements of that problem set. Okay? So thank you very much.